Hello, it's the middle of the summer and quite frankly I need a fun video to slot in around organising a house move, around holidays and the fact I'm starting a PhD at the start of October in Wales. We need something easy and fun. I know, a tier list video, that's what everyone's doing, right? Hopefully this will be slightly less controversial than Simon's stance on fog, #foggang, or Kat's ludicrous idea that turbulence is somehow a bad thing. My name is Thomas Rintoul and this is the Astrophysical Phenomena Tierlist. Okay, rules straight out of the gate. We're working on a 6-tier system. S tier at the top, then A, B, C, D, and then we're skipping E and jumping straight to F tier at the bottom. And this is the phenomena tier list. I'm not going to rank every type of astrophysical object. I don't have time to go through every type of star that we've discovered. That would take far too long and not actually be that interesting. So if an object's doing something interesting, that might be on the list. If it's just an object, then doubtful. These rankings are also based almost entirely on vibes, and my biases will definitely be showing. So to that end, let's talk about accretion. Accretion is a process almost entirely governed by gravity, and it's responsible for some of the most important processes in astronomy, most notably star formation. If something is accreting, that means it's taking on a quantity. Typically we talk about accreting mass, though you can also talk about accreting angular momentum like I did in my master's project. Accretion is the process that allows objects to gain mass by overcoming the limitations of the conservation of angular momentum. It doesn't break the law, but it allows a mechanism to move angular momentum out through an accretion disk, while also allowing mass to move inwards to fall onto a star or a black hole or any other object. Even planets can accrete. This is a fundamental process of the universe that allows almost all of the objects we see in the night sky to form in the first place. For that reason, it has gotta be S tier. As a side note, I did my master's project on accretion. That's totally not influencing my opinion on this in any way. If you want to find out more about accretion, check out the video up in the top right hand corner right now. Moving on from early stars, let's talk about pulsars. These are neutron stars with strong magnetic fields that spin around their axis. While they do this, they send jets of radiation flying out from their poles. We can only see these polar jets when they are pointed in our direction, much like a lighthouse beam can only be seen when it's pointing towards you. Because of this, we see periodic variations in the brightness of these pulsars. These timings are incredibly accurate, which makes pulsars really useful for looking at things in our universe. We've used them to detect exoplanets because the motion of an exoplanet around a pulsar can affect that very precise timing. And they've also been used recently by the Nanograv collaboration to discover a cosmic background of gravitational waves. So because of all this, I want to put pulsars at A tier on my tier list. However, pulsars have been one of the most important objects in astronomy, and as such, the Nobel Prize Committee saw fit to award the Nobel Prize in Physics for their discovery. They were discovered by Jocelyn Bell Burnell, at the time a PhD student. But the Nobel Prize went to Anthony Hewish, her PhD supervisor. So for that reason, the best I can do is rank pulsars as B tier. Come on, Nobel Committee. Now onto some of the biggest explosions in the universe, supernovae. There are two main types that I'm going to talk about. The first is called a Type II Supernova. A Type II Supernova is a bog standard supernova. It's the one you get when a massive star reaches the end of its life. The core has fused all of the atoms in its core all the way up to iron, and then it tries to fuse iron. The main difference when it tries to fuse iron into a heavier element is that iron doesn't fuse exothermically. It takes more energy to fuse iron into something else than that reaction gives out. This means that the pressure support from fusion disappears when this core starts trying to fuse iron. This means that the outer layers of the star can fall in under gravity. They don't have any pressure to support them anymore. When this happens, the temperature rises, the pressure rises rapidly, and you get a runaway fusion event as these layers of gas land on this dense core. This runaway fusion causes a massive outward pressure that blows the outer layers off the star, leaving behind a neutron star, or if it's a really high mass star, a black hole. This explosion releases so much energy over the course of a few months, more than the sun will emit in its entire lifetime, enough to outshine an entire galaxy. Solidly impressive explosion, but fairly common. B tier. The other type of supernova is a type 1a supernova. This kind of supernova only happens for white dwarfs. A white dwarf is a remnant of a star like the Sun. It's a hot core of oxygen and carbon. It's not held up by fusion, it's not heavy enough to have any reactions left. What it's held up with is a quirk of quantum mechanics called electron degeneracy pressure. Basically, the electrons don't want to get any closer together, and that pressure holds this sphere at its size. If it manages to accrete some more mass, say from a companion star or from a gas cloud, it can reach its Chandrasekhar mass, about 1.4 solar masses. When this mass is reached, there is too much pressure from gravity for electron degeneracy pressure to hold it up. It overcomes it and triggers this type 1a supernova that blows the star apart. What makes this interesting is that this event always happens at that mass, so it always has the same brightness no matter where it is in the universe. So if we detect one somewhere in the universe, we can measure the brightness here on Earth, and from there find the distance to that object. It's great for finding the distances to star clusters, to galaxies. It's just a really cool supernova by comparison to the type 2. So I'm going to put this one in A tier. Now, to be quite honest, there are far too many phenomena for me to go through in this level of detail, so let's have a bit of a rapid fire round. First up, hydrostatic equilibrium. This is a really important thing in astronomy, but it's really boring. Essentially, you've got pressure from gravity balanced with pressure outward due to temperature. It's really boring, but it is really important, but D tier. Gravitational collapse. This is what happens if you disrupt a hydrostatic equilibrium for, say, a gas cloud. You can get enough density in one place to cause the entire cloud to collapse under its own gravity. Bit cooler than hydrostatic equilibrium, but again, very common. C tier. Tidal heating. This is another funky effect of gravity. For moons orbiting Jupiter and Saturn, or perhaps planets like them, gravity pulls on them very strongly. Gravity stretches and squeezes these moons as they orbit around their giant planet. These tidal forces cause this moon to heat up from the inside out, and it's what we think is responsible for the oceans under the icy crusts of moons like Enceladus. This process could be responsible for life beyond our planet, but until we discover that, I'm going to have to put this as B tier. Star spots. These are like sunspots, but on other stars. They are regions of stronger magnetic field that appear dark on the surface of the star. Cool, we can detect them, but they interfere with exoplanet observations, and those are cooler. So D tier. Coronal mass ejections. This is basically the sun having a massive burp and ejecting a load of material along its magnetic field lines out into the solar system. They look really cool in observations, and they cause some amazing aurora here on Earth. However, they also cause geomagnetic storms, cause problems for satellites, astronauts on the International Space Station, and can also affect our power grids. B tier for aurora, D tier for the effects. Let's average it out and say C tier. Doppler shift. The Doppler effect is something you'll be familiar with if you've ever heard a siren go past you, and you get that high pitch and then the low pitch as it goes away from you. It's the perceived change in frequency of a wave due to the motion of the source relative to the observer. As an exoplanet orbits its star, you can see the star move as well. As it moves towards you, it appears slightly bluer. As it moves away, slightly redder. And you can see this pattern of slightly more red, slightly more blue repeat periodically as the exoplanet orbits its star. We can detect this. It's really cool for finding exoplanets, but the phenomenon itself is rather pedestrian. C tier. Part of the reason for that rating is cosmological redshift. This is redshift because of the expansion of the universe. Distant galaxies appearing redder because space itself gets bigger. Cosmological redshift is one of the reasons that we know the universe is expanding in the first place. For that, B tier. Sticking with larger scale stuff, galaxy mergers. These are important events that turn spiral galaxies like the Milky Way into elliptical red galaxies. The Milky Way itself will have a collision, a merger with the Andromeda Galaxy in a few billion years. They look really cool in simulations, they're important for giving us elliptical galaxies, they can cause starbursts, so bursts of star formation, but in reality they're not actually that exciting to be a part of. Stars don't collide with each other in galaxy mergers very often, space is just too empty. So there's not really any head-on collisions, you'll just get a bit of a pull of gravity every so often. B tier. Astroseismology. We can detect starquakes. I don't fully understand how we do this, but come on, it's quaking stars. S tier just because that's cool. And final one for the rapid fire round, neutron star collisions. These are less collisions and more mergers. When neutron stars get caught in each other's gravity, they start to spiral around each other, moving closer and closer as they emit gravitational waves. That's got to be A tier, has to be. Moving on from the rapid fire round to something I can't even pretend is cool, dust extinction. Dust by its very nature is boring. Nobody likes it, it's just irritating, it gets in the way of observations, it absorbs high frequency radiation like ultraviolet and X-ray and re-emits it at radio waves, and you've got to use very specific telescopes such as the JWST to be able to see through dust to find out what's behind it. Research into dust is pretty niche, to the point that Brian May, the guitarist from Queen, started his PhD in it, went away and was a rock star for a few decades, then came back and finished his PhD because nobody had done that work in the intervening time. Dust just gets in everyone's way, it's not that interesting. For that reason, dust, and by extension dust extinction, can get in the bin. F tier. From the bane of an observer's existence to one of the best observations ever made, the Cosmic Microwave Background, or CMB. This is the afterglow of the Big Bang. Around 400,000 years after the Big Bang is what we call the epoch of recombination. The protons and electrons in the early universe have got cold enough due to expansion to be able to combine and form hydrogen. When this happens, they release a load of energy, and this is what has become the Cosmic Microwave Background. Over time, this light has been cosmologically redshifted, so it now sits in the microwave part of the EM spectrum. This is one of the most fundamental detections that proves the Big Bang. And it was completely an accident. The original researchers that found this thought there might have been pigeon poop on their detector. Yeah, imagine they're surprised when they got a Nobel Prize for what they thought was pigeon poo. In more recent years, the Cosmic Microwave Background has been observed in more detail, producing this image, and you might think there's a load of variation in that. But the largest variations in colour are 1 part in 10,000. The Cosmic Microwave Background is incredibly uniform, but those little fluctuations are responsible for the structure we see in the universe today. Fundamental physics and some pigeon poo? A tier. From the very long wavelengths of the CMB to some high frequency short wavelength radiation. AGN, or active galactic nuclei. An active galactic nucleus is an accreting supermassive black hole. Supermassive black holes? Cool. Accretion? Very cool, you can see where this may be going. Almost every galaxy has a supermassive black hole in its centre. Our one looks like this in radio waves. When these objects accrete mass, things get very bright very quickly. They are basically a gravity engine. They release energy stored as gravitational potential energy, and through friction and accretion disk, heat up all the gas there and convert that gravitational energy into light. It also grows the supermassive black hole a bit as well. The whole disk glows incredibly brightly. Enough gravitational energy is being converted so that the AGN can outshine its entire galaxy and be one of the brightest objects in existence. A tier. Come on. And if we had 2 supermassive black holes merging, we would get a lot of this final entry on the list, gravitational waves. These are deformations in space-time itself as a result of moving mass. Gravitational waves are a prediction of Einstein's general theory of relativity, and they were considered only theoretical until their first detection in 2015 by the LIGO collaboration. They had used lasers bounced many times along 4-kilometer long tunnels to look for a minute variation in the interference pattern caused by gravitational waves passing over that site. Since that detection, we've had a number of detections of gravitational waves using similar techniques, and recently the Nanograv collaboration, which I mentioned earlier, published evidence of a stochastic gravitational wave background, a gravitational version of the CMB based on pulsar timings. Come on, these have got to be S tier. So this is my tier list. Hopefully you agree with some of it. If you don't, let me know down below or on the Discord. If you'd like some more baseless claims based on the vibe I get from things, then come and join us on the Twitch streams where we sometimes look at the astronomy photo of the day and I give my opinion on that. And in the meantime, make sure to like, comment, subscribe. If you're looking for something else to watch, there's something on the screen, and I will see you in the next one. See ya.